Hey, listen, we're having our third exam on Wednesday, and then Wednesday is also drop day. So I just want to give you a little heads up. I will have that third grade for you before the end of the day, but if you're thinking about dropping, you'll need to see this information. Let me just sort of give you a little heads up on what you're going to get on Moodle on Wednesday afternoon, probably about 2 or so. You're going to get a couple of different things. First of all, I'm going to give you your projected class participation and your EP quizzes. Those are your Moodle quizzes. I'll give you projected values for that, sort of based on what you have now, what I expect that you'll probably get for these in the future. Those aren't certain, right? I mean, they could change. They could either go up or down depending upon how you do on those various tasks. But I'll just try to project it, and I'll try to project it conservatively. That means try to give you a lower estimate for what I think it will be. Okay? And then I'm going to have a series of columns that will say to make an A, to make a B, to make a C, to make a D, and on and on. Right? I did this for y'all last semester, but a few of you weren't here last semester. So these will have different grades. So for example, if in the to make an A column, you have, I don't know, 92%. That means that you need a 92% on exam 4 and a 92% on the final, along with the projected CP, class participation, and those extra practice quizzes. Then that'll give you an A in the class. Okay? So if it's impossible for you to make a C in the class, I'll shoot you an email. But you might want to look at those values and just, see how difficult it is. And if you want to come talk to me, I'll be around that afternoon. But it's going to be kind of tight because I'm trying to get your grades in and then my 202 class, which they take basically all day to grade. So, all right. Does that help a little bit? I'll post those on Wednesday afternoon as soon as I can. I know that you're anxious to know sort of where you stand in the class. All righty? Y'all had a good spring break? Any news from it? We did go camping. Thank you for asking. Yes. Although we didn't go with the kids because, we were all sick. I think I told y'all. But we were all sick, and the kids were sick, and my wife was sick, and I didn't get sick, but, so we didn't go camping. But then my wife and I did go on Monday and Tuesday. It's the first time we've been camping without our kids in like 10 years. It was very nice. Like we like camping with our kids. They're fun, but they just like to do more than we like to do. Like we like to just sit around and be lazy, but they like to go do stuff. All right. But we went to Fontainebleau. Anybody ever been to Fontainebleau? It's nice, huh? And we rode on the Tammany Trace and stuff. It was fun. Okie dokie. Well, let's. We have a few little things to wrap up, and then we'll review for the test on Wednesday. So let's do this quick test. 217. I don't think we've done this one. Which of these mirrors will produce a virtual image under particular conditions? Concave, convex, or flat? All right, just a few more seconds. I'll stop at 38. 38. Okay, awesome. A is right. All of these can make virtual images. You need to know which makes virtual images in which cases. Knowing your ray diagrams will help you with that. You will have a question on the exam that will just show a ray diagram, and I'll ask you which of these rays is correct or incorrect. So you'll need to know the ray diagrams as well. But just knowing sort of what types of images, what types of mirrors produce, and which situations will help you for the mirrors. I'm reading this book. It's about anti-gravity. Can't put it down, man. Okay, let's look at two phenomena. This is new, but it will be on the test on Wednesday. You need to know basic knowledge about this, what causes them, and what the effect is. We have two phenomena. The first is called atmospheric refraction. And in this, the sun appears at dusk even though it is already below the horizon. So the sun appears at dusk even though it is below the horizon. So, you know, if you're over here in Alaska or wherever, and the sun is over here, you shouldn't be able to see the sun because the rays from the sun are blocked by the surface of the Earth. However, because of atmospheric refraction, that is, rays from the sun travel into the atmosphere, and then they're bent so that they come over and you see them. You can see the sun even after the sun has gone below the horizon. And that phenomenon is called atmospheric refraction. It just allows you to see the sun actually after it's physically set. Okay? You follow what I'm saying? Like here, you shouldn't be able to see the sun, but you can because the atmosphere is bending the light rays from the sun, allowing you to see the sun even though you shouldn't be able to because the Earth is actually blocking the rays from the sun. The next is Mirage, which you've probably seen. You see mirages on a hot day. These look like reflections. Like where do you see mirages typically when you're around here? Whereabouts? On the road, right. So if you're out on the road, like that section out in Raceland as you're headed towards 90 past the sugar mill, that's a nice place. It's a nice straight road. It's dark, and so it gets really hot. And then you can see this like shimmering. It looks like reflections, or it looks like what actually? It looks like water. And we think it's water because, well, water reflects light, and so when we see reflections out on the road, we think that it's water. So this looks like reflection, but it's actually a phenomenon that has to do with refraction. Light rays near the hot ground are refracted, or they're bent, right? Refracted is just another word for bent, and they appear to originate from an object that's below the actual object. This looks like a reflection. So you assume that the object, you know, like in this figure, it's a camel. You assume that it's standing in water, which reflects light. All right, so you see an object off in the distance, like this camel, for example. You have light rays that just come straight to you, and then other light rays will go down. Because the index of refraction in the hot air changes, the density of the hot air changes, and that changes the index of refraction, it will actually bend and come up to your eyes like this. But you think that that light ray is coming from a point that is below the surface of the ground, so it looks like a reflection. It looks like the thing is standing in water. The same thing happens out on the road. That's why it looks like it has water out on the road, even on a really hot day. Okay? So know what those two are. They're both phenomena that have to do with atmospheric refraction. The mirages look like reflections, but they're actually due to refraction. You'll see one or two questions about this. Let's see. However, mirages are not a result of reflection. They are purely a refraction phenomena. Let's see. I do have a video. Let me pull it up. All right, I think we have one or two questions here. Let's try these. Which of these physical phenomena is the cause of a mirage? Is it refraction, reflection, diffraction, or interference? All right, I'll stop at 25, 25. Let's go ahead and try this next one. Let's see. So this one is A. Very good. Good job. 100% easy question, right? But you could see a question like this. So just make sure you know what causes these things. And what causes a mirage you see while driving on a road? Looking at this question right here. Goodness. You okay, Ryan? Was that Ryan? Okay. What causes a mirage? Okay, just a few more seconds. I'll stop at 28. Okay, awesome. A is right. It's the refraction of light and warm air is what causes a mirage, like you just said. And then if the Earth's atmosphere no longer existed, how would the time of sunset be affected? All right, I'll stop at 35, 35. Okay, that's awesome. A is right. It'll come up, or the sunset will occur earlier because the sun will drop below the horizon and then you won't be able to see the rays. But if you have the atmosphere, it drops below the horizon, but you still see the sun. So next time you see the sun, you can tell your friends, like, hey, the sun's not really there. It's actually below the horizon. Right? All right, awesome. The other night, it's like I stayed up all night long because I was wondering what the sun did. Like when it comes up in the morning, what happens in the morning. And then stayed up all night, and then it dawned on me. Okay. Let's do that. That's the end for the exam, which is going to be on Wednesday. It's kind of a nice breaking point, but let's spend some time just going over stuff. We will have the help session this Thursday at 3. I might move it to a different time, okay? Oh yeah, the exam's on Wednesday. I don't think I can do it on Tuesday. I'm sorry. I'll have to check and see. I might be able to do it on Tuesday. Would y'all come on Tuesday if you would like that? Okay, let me see what I can do. I can't promise it. I'll have to see. I think I have a lot of stuff going on. But I'm always available to you, so if you need help, you can come to my office as well. Well, let's spend some time going over what we have for this test. Let's see. I think we're doing all of Chapter 5, 6, and this first part of Chapter 7, right? So Chapter 5 was magnetic fields. It's going to be roughly, I think it's roughly half magnetism and half light. So I'll give you a quick rundown of the topics that you'll see. So in Chapter 5, you just need to know basic stuff about magnets. You'll have 1 or 2 questions about, magnets, their poles, monopoles don't exist, the whole thing about magnetic domains. Just sort of go back through your notes and look at those various things about magnets. Most of that you probably knew before you even came in. The Earth's magnetic field. You remember that the geographic and magnetic poles are switched, that the southern magnetic pole is at the North Pole and vice versa. Also, we talked about things like the Aurora Borealis. Just go back through your notes and remind yourself what causes that when these charged particles come in onto the Earth's magnetic field lines and enter the Earth's atmosphere. They cause this glowing light. And also that the Earth's magnetic field protects us from the solar wind. Talked about that early on in that chapter. You'll need to know how to calculate the force due to a magnetic field. That's this QVB sine theta. Look back, we worked through some problems where I give you Q, I give you V, I give you B, and you have to calculate what is the force on that object. You'll also, of course, need to do your right-hand rule, so make sure you're good on your right-hand rule. I expect we'll do some. You guys probably have questions still about that, or are still struggling a little bit maybe. So the right-hand rule for that, you'll have a number of right-hand rule questions, right? We had several applications of the right-hand rule, so we'll see that on the test for sure. You'll also need to know the magnetic force on a current carrying wire. It was very similar. This F equals ILB sine theta. It works basically exactly the same way as the QVB sine theta. And you know the right-hand rule for that situation too. Torque on a current loop. mass spectrometer, know what causes it to work, know how to calculate the charge to mass ratio. The magnetic field of a long straight wire. I think that this might have been on that day that we were out, is that right? I don't remember. I think it was, yeah. So make sure that you're up on that. If not, you can come see me. I'll be in my office. We'll try to do a help session tomorrow. Magnetic force between two conductors. A lot of these are just knowing what the equations are and knowing where the equations are on the equation sheet, which they are there, how to use them. And then current loops, the magnetic field of a current loop. All right, this is a solenoid switch. Again, that was on that day with the screencast when we were out that day. So if you have questions, we can come back and revisit that. Let me just sort of cover all the various topics. All right, Chapter 6 was on reflection and refraction. You do need to know just sort of the basic history of light, or the history of, is light a particle or wave? Know the big players, that would be Newton, Huygens, Young, and Einstein, and how and why they thought that light was a particle or a wave. That's in your notes, but you'll probably need to answer a question regarding that, whether light is a particle or a wave, and why they thought it was a particle or a wave, those particular people. Then reflection. Likely you'll have a question where I have, a couple mirrors with a light ray, and I ask you, what is the reflected ray of the second ray, where it reflects off of this second surface right here. We did one like this in class. I think you have a homework problem like that as well. If you look back at old exams, you can see that as well. It's really just knowing your geometry and your triangles. Also refraction. I have several about this, both quantitative and qualitative. That is, which way does light bend when it enters a medium? Does it bend towards the normal or away from the normal? And then also being able to use Snell's law, the law of refraction, n1 sine theta 1 equals n2 sine theta 2. Doing that kind of business. So you'll have both calculations and situations where I tell you n1 n2, and I ask you, does it bend towards or away from the normal? You could also see a problem like we had in class where you actually have 3 media and ask you to trace the rays through those media. We did some problems like that in class and on the concept test. Also regarding refraction, remember that light slows down when it enters a medium, and that my index of refraction is the speed of light in a vacuum divided by the speed of light in that medium. That's C over V. Need to know the EM spectrum, electromagnetic spectrum. Right, it goes from radio up to gamma rays. Know what happens to the energy, the frequency, and the wavelength in each of these. This goes from long wavelength to short wavelength, from low frequency to high frequency, low energy to high energy. I think that you guys probably know that mostly, but you might want to review your electromagnetic spectrum. Be able to put them in proper order of wavelength, frequency, or energy, any one of those three. You know about prisms, version of prisms. Remember, that was due to the prisms disperse light into its different colors because the index of refraction depends upon wavelength. It changes for different colors, so it bends different colors of light different ways. And then in Chapter 7, we only have half of Chapter 7. We have flat mirrors. That was, Q equals negative P, M is equal to positive 1. The big thing on this is knowing your signs. There were some tables in your notes for magnification, Q and P and F and all that. Just make sure that you're up on those signs for what all those various values are. Then we also have spherical mirrors, concave and convex. You'll have to use the mirror equation, 1 over F equals 1 over Q plus 1 over P. And then also be able to calculate the magnification. That's that negative Q over P. Also remember that magnification is HI over HO. These can be a little tricky, so I know that you might think that you got it down, but I would certainly go back and practice some of these problems, either in the homework or the old test. I would look back especially at the old test, because sometimes they can be a little tricky, because there's information that you know that's not stated in the question. And you know it because of the type of image that's being formed. For example, whether it's virtual, whether it's bigger or smaller, that sort of thing. Knowing your mirrors and knowing what types of images they form will really help you. So knowing your ray diagrams will help too. Honestly, I'm not going to give you one of those really difficult ray diagrams like the, I don't know, what was a difficult one? The concave when you're inside the focal point. That's a pretty hard ray diagram. It'll be a simpler one than that, but you'll need to know those basic rules for drawing rays. However, you do need to know what type of image forms with what mirror. So for example, with a convex mirror, if that's my object, this forms a virtual, upright, smaller image. And then with my concave mirror, I have 3 different scenarios. I can be outside the focal point, at the focal point, or inside the focal point. Outside the focal point, I form a real inverted image. At the focal point, I form no image at all. And then inside the focal point, I form a virtual, upright, bigger image. So knowing those different types of images that are formed will help you. I'll show you some problems like that where, like a word problem where you have to do some calculation, but you also need to know these various scenarios to actually know how to solve the problem. I think, oh, and then the atmospheric phenomena that we just did. Mirages and the sun setting. I think that's it. Yeah. Also, don't forget for mirrors that the focal length is also the center of curvature divided by 2. Remember that for convex mirrors, that's these right here, they have a negative focal point. These have a positive focal point. I won't tell you the signs for that. You'll just have to know, well, gosh, this is a convex mirror, and so it has a negative focal point. Sometimes I won't even tell you that it's a convex mirror, but I'll tell you, say, that the image is upright and smaller, and then you would know right away, oh, well, that must be a convex mirror, because no other mirror can form an upright, smaller image. Okay? What do we need to spend time on most of all? What questions do you have particularly? There's the right-hand rule, there's the mirror equation. Yeah, thanks. You want to take it right now? Just take the exam right now. Okay, well, let's do some right-hand rules. We'll jump right in. Let me just start a new page here. Is this going to insert a blank page here? Awesome. Okay, so imagine, I think we had a question like this. Imagine that I have an electric field that is in this direction. This is my electric field. I have a positive particle like this. It travels through that electric field undeflected. Pretty sure we had a question like this. And I want to know, what is the direction of the magnetic field? What is the direction of the magnetic field that causes this particle to travel undeflected? Now, several things you have to think about here. First, you have to think about what is the direction of the electric force, and then what is the direction of the magnetic force, And then what is the direction of the magnetic field that causes that magnetic force? What is the direction of the electric force in this case? Up or down? Is this up? Yeah, up. It's up. The electric force, because it's a positive particle, is going to be up. So the electric field and the electric force are in the same direction. So the magnetic force is also down. So then this becomes a basic right-hand rule problem. I have a V in this direction. I have my F, B in this direction. That's my force due to my magnetic field. And then I want to know what is the direction of the magnetic field. Let's just try it as a clicker problem, okay? Is it left, right, into the page, out of the page, or up? What's the direction of the magnetic field in this case? Make this a little bit longer. All right, I'll stop at 58, 58. Okay, doing pretty well. All right, folks, I just want to point out here, most of you got this right in the sense that you didn't answer the really wrong answers. The really wrong answers are A, B, and E. But just remember that you can always limit your answers to just one or two by remembering that they have to be orthogonal. So if the x-axis is taken up, the y-axis is taken up, so it has to be either plus or minus z-axis. So it has to be C or D, because those three vectors are always orthogonal. They always are perpendicular to one another. So here I have V is in that direction, so right. F is down, like that. And so the magnetic field has to be coming out of the page. So D is the right answer. All right, you'll have some others, like for example, let's say that I have a negative particle. It's traveling in this direction, and then it enters into this mass spectrometer, and it follows a path that looks like this. What is the direction of the magnetic field that has caused that motion? Let's see. Let's use the same options over here. We'll do it as a clicker question. What is the direction of the magnetic field that has caused that motion? There's some magnetic field in this region. What is it? So I have this negative particle that's traveling into this mass spectrometer. All right, do about 10 more seconds, so. Remember to think about which ones can you eliminate, which ones cannot be the answer. I'm going to stop at 102, 102. Okay, so you certainly want to go back and review the right-hand rule if you're having trouble in these, but let me just show you here. My velocity vector is in this direction. The force vector is going to be down like this, right? Because once it enters here, it pulls it down. And so the magnetic field, you would think, should be out of the page, but it's a what? It's a negative particle, so you have to not out of the page, but into the page. So C is the right answer. All right, don't forget, too, that you also have another application where, say, if I just have a wire like this, the magnetic field, I let my thumb go in the direction of the wire like this, and then my fingers wrap around and show me how the magnetic field folds around that wire. So in this case, it's going to go into the page, out of the page, into the page, out of the page, into the page, out of the page. I also like to ask questions like, well, gosh, what if I have a particle that's going in this direction? What direction is it going to travel? So you have to use two applications of the right-hand rule in that case. Here it's entering into a magnetic field that's into the page, so what's that? It's going to go down, right, like that. If you look back at the old test, you'll see questions like that, but make sure that you're able to do both of those. Alrighty? Any other particular questions about the right-hand rule? Okay, those are sort of the difficulty level you should expect to see on the test. It's not going to all be just like the simplest ones that you have, but some more complicated like that. You'll have a couple of simple ones as well. Okay, you have to do all those calculations, like I said, the QVB stuff, the ILB stuff. What about the mirrors? How are you guys on the mirrors? Let's go through some of the tests, and we'll take a look at some. Look at the old exams. Remember, with the old exams, if you run into lenses, you just stop right there. Let's see, exam 3 probably. Oh, also, I did forget to mention this, but you will see total internal reflection. I really sort of consider it just a special case of the law of refraction. Total internal reflection, like this, where you have a fiber optic cable. Either a calculation of the critical angle or asking you questions about how the indices of refraction have to be related to one another. That you have to move from a high index to a low index, like from glass to air, for example, or water to air. Let's see, these are all chapter 6. Let's look at the next one. Okay, you will have one like this where you have to pick out the correctly or incorrectly drawn ray. Can y'all pick out the one that is drawn incorrectly? Let's see, I have this one goes parallel to the axis, and then it looks like it goes through the focal point. That's number, oh yeah, that's number 3, thank you. Is that correct? Yes, parallel to the axis through the focal point. Number one goes through the focal point parallel to the axis. That's correct. And number 2 looks like it goes through the center of curvature and parallel to the axis. Not correct. So know your ray diagrams enough to be able to pick out what's correct or incorrect in that way. Here, like number 1, a mirror produces an upright image. The object's 2 centimeters high and 2 centimeters high. The image is 8 centimeters high. The center of curvature of the mirror is 16 centimeters. Where is the object located? This is what I'm talking about when you have information in this problem that's not stated explicitly. So what type of mirror is this? Is it a convex or a concave mirror? It's con what? What do you think? Somebody said something over here. Ryan, was that you? Or Janie? What did you say? Concave is right. We know it's concave because the image is bigger than the object. The image is 8 centimeters high. The object is 2 centimeters high. So my magnification is 8 over 2 equal to 4. Further, it doesn't say this, but further I know that it's positive because a concave mirror, when it produces a bigger image, is always going to be positive. It's always going to be upright. So that's important because the center of curvature here is 16. That means my focal length is positive 8. Now if it was the other way around, like if my magnification was less than 1, then I would have to say that my focal length would be negative 8. But you wouldn't know that right off. If it was a convex mirror, you'd have to recognize that the focal length is negative. So when you see these questions, just stop for a second and take a big deep breath and think about, what kind of mirror am I dealing with? What is the scenario? And think back through those 4 different scenarios with our spherical mirrors. Okay, where's the object located? Well, I know that 4 is equal to negative q over p. I'm looking for p. I know that 1 over f equals 1 over q plus 1 over p. I'm looking for P, so I have to do substitution here. I say 4 is negative Q over P. So Q is equal to negative 4P. And then I take this and I plug it in here. So I get 1 over F equals 1 over negative 4P plus 1 over P. And then I would solve that for P. You could see a substitution problem. You probably won't, you'll just have one if you have it, but you could see a substitution problem like this. I don't remember if I put one on there, but I should be able to solve a substitution system of two equations like this. I think that y'all can. But just be careful on how you're doing it when you do the algebra, because you can't get tripped up. All right? Is that okay? Let's just sort of scroll through here, and you'll holler out if you see anything that you want to take a look at. Convex mirror. Here, you won't have any lenses, but what kind of mirror would that be? What kind of mirror would this be, number 3? That's a convex mirror, that's right. It is a virtual image because it's on the opposite side of the mirror, like in Poltergeist. Those are virtual images. It's smaller, so we know it's convex. Let's see. Let's go back. Let's look in the back of the book, actually. I don't think we've done any of those. All right, you'll have stuff about the EM radiation probably where you organize them, indices of refraction like this, fiber optic stuff like this. I'm on page 320, 321. Mass spectrometer where you have to pick out the unknown particle, speed of light in a medium. Any of these stand out to y'all? Want me to work through? This is 322. Y'all flip through there and let me know what you see. Okay, looks like we're going up to 12 on that exam. Oh no, there are some other, I'm sorry, there are some. Here we have number 15 as well. Uh, 16, 17, 18, 19. Any questions about those, y'all?
So the fiber optic so the class can go outside.
Right. For fiber optic, I always get this mixed up, but if you think about a fiber optic cable, it's really just a piece of glass, right? That all you really need is glass with air. And so I know that the index of refraction of glass is bigger than air, right? The N of air is 1, index of glass is like 1.5, so it's always moving from a big index to a low index. Now in fiber optic, sometimes they'll actually put a sheet around it, but it always has to have a lower index of refraction. Okay? Questions, y'all? I feel comfortable with this stuff? You just need time to prepare on your own. Yeah, Ryan. Okay, let's look. Is it this one right here? Oh, the previous one? What page is it on? Okay, yeah, so you'll probably see something like this. Here we have a coil of wire that sits inside a magnetic field. The magnetic field runs from north to south. And I want to know what direction is it going to rotate. I give you the current direction. The current travels like this in there. I just want to pick one side of it and ask myself, what is the force on that current carrying wire? So here my current is out of the page. My magnetic field is to the right. And so my force on this side is going to be up. It's your right-hand rule application of your force on a current carrying wire and a magnetic field. So the force on this side is up. The force on this side will be down. So it's going to be moving in a clockwise direction. So B would be the right answer. We had this in the concept test, but you'll probably see something like that. I don't remember. It's been a while since I made out the test. But I'm pretty sure you'll see stuff like this. All right. Anything else, John? You want to move on to lenses? Okay, we'll stop there. I'll try that out, but I can't guarantee it. I'm sorry. So we'll try to do it tomorrow. I know that y'all want to do it. But Wednesday, there'll be a seating chart on the door. It'll be different from last time. If you have any questions, let me know.